Hi, everyone. Today I want to talk about Bayes rule or Bayes theorem or Bayes formula. Let's have a look at an example first. Suppose you want to select two cards from a standard deck of 52 cards. If you know the second card is a heart, what is the probability that the first card is a heart? If you know that the first card is a heart, then the probability that the second card is a heart is quite easy to find. It's kind of natural, okay? You know the first card is heart. Oh, by the way, we're talking about selecting two cards without replacement. You pick two, you pick one, you don't put back, okay? All right, so you know the first card is a heart. So totally you have 12 hearts left, 12 hearts left. And then at the beginning of 52 cards and one card is gone, you have 51 cards totally, totally 51 cards left. So the probability of H2 given H1. H1 means the first card is a heart, H2 means the second card is a heart. So it's just 12 out of 51. Okay, so this is pretty easy to find. Now, the question is asking, knowing that the second card is a heart, what is the probability that the first card is a heart? This kind of probability is usually called a posterior probability. You know something happened later and try to figure out the probability of something happened earlier. One way of analyzing this type of problem is to draw a tree diagram. So let's do that. You have the first card being a heart or a non-heart. So we put two letters there. Okay, the first card is a heart. Let's put 1, so just to show that the first card is a heart. And the complement, the first card is a non-heart. And then you have a second card. Okay, so you have a second card being a heart and the second card being a non-heart. Similarly, in the second case, you also have two cases. So let's put H2 here, H2 complement, H2 here, H2 complement. And then we put those probabilities. Okay, so first of all, the probability of getting the first card, a heart, is 1 out of 4. Okay, you have 4 suits. Each suit has 13 cards, 13 out of 52, or 1 out of 4. And the probability of getting a non-heart for the first card is 3/4. And then this probability, we put it here, is a conditional probability. Okay, this is something I want to emphasize. So this one is actually the probability of H2 given H1. All right, so the first card is a heart, and yeah, we did that. You have a 12 out of 51. So we put it there. Okay. You have a 12 out of 51. And then if the first card is a heart, then the second card being a non-heart, the probability would be 39 over 51. 39 comes from 51 minus 12. Okay. And then if the first card is a non-heart, so you have 13 hearts left out of 51, and then 38 non-hearts left out of 51. I want to emphasize again. Okay, these probabilities. Let me draw what? Draw a rectangle, I guess. So these probabilities. They are conditional probabilities. Okay, they are conditional probabilities. You need to understand the meaning of these probabilities, okay? For example, 13 out of 51 is actually the probability of H2 given H1 prime. Okay, so this is the tree diagram. Now let's try to find the probability in the problem. Okay, so let me erase this part. Okay. So how do we study that? We're looking for the probability of H1 given H2. Okay. Based on the definition of a conditional probability, right? So usually we say a probability of A given B is probability of A intersect with B divided by the probability of B. Okay, that's the definition, provided that the probability of B is not equal to 0. Okay, so we're going to use that probability of H1 intersect with H2. Sometimes the intersection notation can be neglected. Let's write it anyway. And then we use the product rule of probability. The probability of A given B equal, no, not that one. The product rule of probability. Probability of A intersect with B, that is probability of A given B times the probability of B. And you would see these two equations are really the same, but they serve different purposes. This one is a definition of a conditional probability. You know the probability of intersection, you find the conditional probability. While this one is, you know the probability, conditional probability, you try to find the probability of intersection. They just serve different purposes, and both are important, so we give them, well, the first one is definition, the second one is a name. There's a rule, product rule of probabilities. Okay, so you don't want to condition on H2 because now you're going back to the original one. So instead, we're going to use this conditional probability. Like I said earlier, the probability of H2 given H1 is relatively easier. Well, it's quite easy actually. Right? You know what's going on in the first step, then it's clearer for the situation in the second step. We know that. We need to figure out the probability of H2. Here comes the total probability. So H2 can come from the first case, which is that the first card is hard. It can also come from the second case, which is the case that the first card is not hard. So there are two possibilities. We actually need to add them. So that's right. Probability of H2 equals the probability of H2 intersect with H1. That comes from the first one. Plus the probability of H2 intersect with H1 complement. Okay. It's really just a union rule, but the union rule, the intersection part is empty because you have H1 prime. They are like mutually exclusive. So the minus part is gone. The probability of the intersection is 0. I'll talk a little bit more about that a little bit later, okay? But for the moment, we work with probability of H2 like this. And then we use the product rule of probability again, conditioning on the first step. All right, so that's H1 prime. Now you can see all the probabilities are on the tree. Probability of H2 given H1, that's 12 out of 51. And the probability of H1 is 1/4. This is what? 13 out of 51. And this is 3/4. So everything's there. So now we are able to figure out the probability of H1 given H2, which is posterior probability. Okay. I'm going to erase the second row sort of, and have more, so I have more space. Okay, so we do the probability of H2 given H1, just copy the numerator. And then the bottom is kind of a sum, okay? Sum of the products. Right, so we write that. So everything is given. H2 given H1, so you have a 12 out of 51 times 1/4, and then you copy that, and then you have a probability of H2 given H1 prime. You have 13 out of 51 times 3/4. I simplify it. You multiply the numerator and denominator by 4 times 51. You have 12 out of 12 plus 39, which is 12 out of 51. You see, this is actually the same as what we have here, 12 out of 51. And this is a little bit special. This problem is a little bit special. We would call H1, H2 like they are interchangeable and exchangeable. So we literally figure out the posterior probability and also the formula actually. All right, so let's work with the give the formula. Before I give the formula, I wanted to talk about the partition. So in the first slide, let's say this one, the probability H2 equals the probability of H2 intersect with H1 plus the probability of H2 intersected with H1 prime. In general, suppose we have a bunch of sets, okay, a bunch of sets. Let's say A1, A2, A3, and so forth. Let's say A sub n. These sets, I'm going to give them two properties. One, they are mutually exclusive. So AI intersect with AJ is empty for any ij not equal to, if I not equal to j. If I equal to j, then AI just AI, so maybe they are not empty. Those AIs are not supposed to be empty. This is the first property, that they are mutually exclusive. Actually, a pairwise disjoint. Okay, this is the first property. The second property is the union of everything, of all these AIs, I from 1 to n. So this is like a union notation for a bunch of sets. It's the total set, the universal set. Okay? U is the universal set, is everything. Okay. And then these AIs are called a partition. So these A1 dot 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 A sub n, they are called a partition. Maybe you can say the set of sets is a partition. It's a partition of the universal set. All right, so when we talk about partition, remember there are two things. One, pairwise disjoint. Second, two, the union is the total set, is a whole set. Partition. Now, if I introduce another set, any set, say B. Okay, let's put a B somewhere here. Let's say a nice circle. So something like that. So let's call it B. Obviously, let's work a little bit more. Okay, so B is the same as B intersect with the total set union, the universal set. But the universal set, we say it's just the union of a bunch of I, so AI, so union with A2, union with dot dot dot, union with A sub n, and then use the distributive law, B intersect with A1. If you're not comfortable with so many notations, yeah, I guess you can skip this part. But if you wanted to know a little bit more about sets, I think it's a good opportunity for you to review. Okay, so B equals the union of the intersections. So basically B is the union of this one, and this one, and this one, and this one, and so forth, and possibly n of them, okay? Now, the probability of B equals the probability of this bunch of unions. We're not going to use the general union rule because it's a little bit more complicated. We only need to take notice that they are mutually exclusive because AIs are mutually exclusive. Yeah, this property, right? So all these intersections, they are mutually exclusive. So we can simply add. So that's why we have this thing plus. We only need to add. We don't need to consider the intersections because intersections are empty. Okay, so we have this total probability of B with respect to a bunch of partition, okay, a bunch of sets which form a partition. All right, so that's the theory behind the denominator we just calculated earlier. All right, so let's talk about the formula. I'll give you a relatively more general situation. All right, so suppose the first part of the tree has a bunch of things, okay? So let's call them A1, A2, A1, A1, A2, dot, 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 and you have A sub n. Okay, they form a partition. Right, all these probabilities would have to be 1. And then you have the second layer of the tree. Let's call B and B prime. All right, B and B prime. B, B prime, B, B prime, B, B prime. And here there are a bunch of them. Actually, we don't need to, well, I mean, it could be that you have a B1, B2, B sub m here, but it's unnecessarily unnecessarily complicated for our purpose. So we're gonna just treat B and B prime. It doesn't really matter. You have these sets here. Okay. And then you assign all these probabilities, okay? You assign the probability here, 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 and so forth. And then you have conditional probabilities to complete the tree, okay? And then we're looking for the probability of some AI, maybe A1 or AI. I could be from 1 to n, given B. Okay. Again, this type of probabilities are called posterior probabilities. Knowing something in the second part of the tree, we try to figure out the probability of something happening in the first part of the tree, the posterior probability. The formula is given by sort of a big fraction. Okay. The numerator would be the probability of B given AI times the probability of AI. And the bottom is the sum of a bunch of products. The probability of B given A1 times the probability of A1 plus dot, 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 plus the probability of B given A sub n times the probability of A sub n. Okay, assuming all these conditional probabilities would make sense and the bottom is not 0, that's usually the case. That is the Bayes formula. Okay. So I think that's the theory about the Bayes formula. And let's see, let's look at an example. I was thinking to separate the video into two parts, but it's kind of awkward without giving any example. So let's move on. Right, so this is the problem. A credit card company offers two types of cards, a basic card B and gold card G. Over the past year, 40% of the cards issued have been of the basic type, and automatically, 60% would be of the gold type. Of those getting the basic card, 30% enrolled in an identity theft plan, whereas 50% of all gold cards holders do so. If you learn that a randomly select card holder has an identity theft plan, how likely is it that he or she or they has a basic card? Once you realize it's a base problem, I highly recommend that you should draw the tree diagram. Okay. While you draw the tree diagram, you need to figure out what you should put in the first part and then what should you put in the second part of the tree. You would get some information, some hint from the problem. First of all, 40% of the cards issued have been of base type. This is not conditional probability. So, like I said, for the second part, you see those probabilities that they are conditional probabilities. So that will probably give you a hint that basic card and gold card should be in the first part of the tree. And also you look at those probabilities. 30% of those getting the basic card, 30% enrolled in an identity theft plan. So this 30% is actually a conditional probability conditioning on basic card. That also gives you a hint that the first part should be basic card or gold card, while a second part would be like identity theft plan. Okay, maybe PL, I don't know, some kind of notation. P is maybe T, okay, theft plan. Or maybe I, it doesn't really matter. As long as people know, you know, and you make clear, then we would know. That should be okay. Okay, so this is the tree diagram. And then we mark all these probabilities. Among these people, 40% are basic. So let's put 0.4 here and then 0.6 for the gold card. Of those getting the basic card, 0.3 would enroll in an identity theft plan. The probability is 0.3. Okay, it's conditional probability. And then 0.7 for those who get the basic card. How do I say? So 0.7 is the probability that somebody would not enroll in an identity theft plan if that person is a basic card holder. Similarly, for gold card, you have a 0.5. And that's pretty straightforward. And now, what we're looking for, if you learn that a randomly select card holder has an identity theft plan, so this is known, T is known, so T is known. That will give us this probability. How likely is the probability? It's a conditional probability, condition on T. And we're looking for the probability that this person has a basic card B. Okay, so from the question asked, we know we express it as this conditional probability. Then we ask ourselves, if this is a posterior probability, Well, conditional on something here, we conclude, yes, it is a posterior probability. Then we're going to use the Bayes rule. Okay. When you use the Bayes rule, it's kind of a, when you use it, it's actually very easy. I usually tell my students, oh, I just circle certain things. T, right? T is given, you circle that, and you're looking for the probability of B, which is here. So the formula really tells us you can do this very quickly. You multiply this number 0.4, 0.3, and then you add 2. Here you have 2, so you have add 2 products. Okay. 0.12, 0.12 plus 0.3, 0.42, 1242. I don't know what that means. That's a number divided by 2 out of 7. Okay. You can make a decimal number. That's okay. Yeah. All right. I think that's a simple example. Usually we ask you that, but I usually ask more than that. The reason is that I don't want you to just have a sort of thinking that once you see a Bayes rule, a Bayes theorem problem, that everything you should use a Bayes rule. That's not the case. So I want to give a problem which I will ask a bunch of things instead of a posterior probability. I will ask you a bunch of things. And that gets the problem, it makes the problem a little bit harder because you really need to know what I'm asking. Okay. Sometimes it's a conditional probability, sometimes it's not. Sometimes a posterior probability, sometimes it's not. So let's have a look at an example like that. Okay, actually, well, I do have a bunch of things here. I didn't realize that. Well, why don't we do that? Okay, so I don't need to work with another problem. Let's continue that. Okay. Let me draw the graph again. Okay, so it's a tree. All right, now I'm asking you to find the probability that a randomly selected card holder holds a basic card and has an identity plan. Okay, so ask yourself, what is this probability? The probability is conditional or not? Well, we have sort of a keyword for, well, the keyword here is and we talk about the keyword and means the intersection. So it's at intersection. It's a probability of a basic card intersect with T having an identity theft plan. It's a condition. It's not a conditional probability, so you really should not use a Bayes rule. This is the probability intersection. We can use the product rule, the condition on B instead of a condition on T, which is posterior probability, and it's a little bit harder to find. You're going to use the Bayes rule. So instead of doing that, we use the product rule and condition on B. Okay, so this is product rule of probability. And then 0.3 for the conditional probability of T given B, and then you have a 0.4. So this is 0.12. That is the answer, okay? It's not a conditional probability. All right, let's move on to the next one. Okay, it's a little bit G. I wanted to put this tree somewhere. So, all right, I can get rid of these things. All right. Now this one, what is the probability that a randomly selected basic card holder doesn't have an identity plan? It's a little bit hard to figure out. I mean, in the sense that what is this probability? How to express it mathematically? It is not and okay, it is not basic card, doesn't have a theft identity plan. It's not that. Actually, you are selecting somebody who holds a basic card. And what is the probability that this person doesn't have an identity plan? So actually, it is a conditional probability, but conditioning on the basic card holder. And we're looking for the probability that this person doesn't have identity theft plan. This is what we're looking for. Okay, it's not a union, not just. It's also different from the probability of T prime, because the probability of T prime can be from the basic card holder or a gold card holder. But here you are selecting from a basic card holder. So it's actually a conditional probability. And then you ask yourself, is this a posterior probability? If it's posterior probability, then you should use Bayes' rule. Here you condition it on B, we're looking for the probability of T prime. So it is not a posterior probability, okay? It's not. So you don't need to use the Bayes rule. In fact, this is simply 0.7 from the tree. That's what 0.7 means. It's a conditional probability of T prime given B. All right, so I require you to know the meaning of all these conditional probabilities. You need to know that. All right, so this one is actually a conditional probability, but not a posterior probability. You can find the probability directly from the tree. Okay. All right, what's the next one? What is the probability that a randomly selected card holder doesn't have an identity plan? Okay, so this person is just a card holder, sure. It doesn't say this card holder is a basic card holder or gold card holder. So there's no information there. So in that sense, it's not conditioning on B or conditioning on G, it's just a card holder. And we're looking for the probability that this person doesn't have an identity plan. So it is not a conditional probability, okay? So no, it's not conditional on B, not conditional on G. We're simply looking for the probability that this person doesn't have any identity plan. Okay, so you need to figure out it's actually not a conditional probability, it's simply a probability of T prime. So how can we do that? Well, it's not in it's Bayes formula. You should not use a Bayes formula. It's not there. You sort of need to understand how we get the probability of T in the first place, right? It's the total probability. So you use a similar argument to find the probability of T prime. It can be from this branch, and let's see, I should include primes. It comes from this branch or comes from this branch. There are two cases. It's a union. You need to add two probabilities. And these two are mutually exclusive. You simply add. You don't need to subtract the probability of intersection. So this is just the probability of B intersect with T prime. Oh, you switch order, doesn't really matter. And switch order B and T prime, that doesn't really matter. And then use the product rule. So you have a 0.4 times 0.7. I think let me rewrite the product rule. Okay, so probability of T prime given B times the probability of B plus the probability of T prime given G times the probability of G. And then you plug in the numbers from the tree. You have a 0.7 times 0.4 plus 0.5 times 0.6. So you have a 0.28 plus 0.3, 0.58. So that's the answer for this one. Okay. All right, I think that covers most of the situations I want you to know. So that's about what I want you to know. Maybe I'll ask different things, but really just there's these types, one of these types. Okay, that's for today. I hope that helps. I'll see you the next time. Bye-bye.